All right, wonderful. I think I'm recording now. Since today is our first day of Calculus 3, I want to start things off relatively easy. So I want to remind ourselves of a very basic mathematical fact that 3 is actually equal to 1 plus 2. Now, of course, that's something you knew like forever ago. That's not really important news. What are you trying to get at here, Dr. Manley? Well, the way we're going to think about Calculus 3 is instead of thinking about it as a new thing, we're going to think about it as Calc 1, but then we're doing it again. So this is Calc 1, 2, or Calc 1, the sequel. So this class is going to have a lot in common with Calculus 1. All right, so what is it going to have in common with Calculus 1? Remember, in Calculus 1, we began by doing things with a review of algebra and trig. And then we moved on to talk about something called limits, or what happens as the input of a function approaches a certain number, what happens to the output. And from limits, we were able to talk about two different operations, derivatives, and then we had integrals. And then finally, these were inverse operations, and then we saw how they related together through the fundamental theorem of calculus. So this effectively showed that the derivative and integrals are inverse operations. All right, now, what is the overall theme with all of this stuff? Let me remind you, if you didn't have me for Calc 1, calculus is the mathematical study of change. We live in a world where so many different things are changing, and we can model these mathematically using calculus. So what does this stuff have to do with change? Remember that the derivatives represent the instantaneous rate of change, and that integrals represent the total amount of change. Now, bear in mind, all of this applied to single variable functions, y equals f of x. So we have one dependent variable, y, and an independent variable, x, right here. So this was all, we learned about all of this stuff for single variable functions. Now, what we're going to be doing in Calc 3 is Calc 1 with a 2 is we're going to do essentially the same thing. We're essentially going to repeat this in the same order. The only difference is that in Calculus 3, we're going to be looking at functions that depend on more than one variable. So rather than seeing y equals f of x, we're instead going to see maybe a z as a function of x and y. And there's no reason why we can't expand further past this. We could have maybe u as a function of x, y, and z. And as we'll see, most of the things we learn in this class apply to functions of any number of variables, 2 or larger. So you kind of get all of those for free, or for free. Anyways, so we're going to turn our attention to the study of change of functions that look like this right here. All right, so in the same way that we did a review before, we're not going to quite do a review in the beginning, but we're going to get acquainted with three-dimensional space. So kind of like how with functions of x, we kind of put these curves in two-dimensional space. In Calculus 3, when we have two independent variables and one dependent, we're going to have to do things in three-dimensional space, which I'm going to talk about in a second once I'm finished here. So that's going to be a little bit different, and I imagine most of you guys probably haven't seen that in high school before. So we're definitely going to not quite review it, but we're going to go over it. But you'll see a lot in common with this as with the normal XY plane. Once we do that, then we're going to learn about limits for multivariable functions. Then we're going to talk about the multivariable functions version of derivatives. And then we're going to talk about the new version of integrals. And then finally, we're going to see that there in fact are higher dimensional versions of the fundamental theorem of calculus that apply to functions of multiple variables. So we're going to have new versions, and it's versions plural. So that's going to be kind of interesting. We're going to have new versions of the fundamental theorem of calculus, FTC. So essentially, whenever we're doing something in Calc 3, we probably already did something similar to it in Calculus 1. So this is my big piece of advice to you. If you're ever struggling on a new concept in this class, think about what calculus 1 concept this matched up with. So for example, if we're working with a derivative in Calc 3, it's going to mean a similar thing to what derivatives meant back in Calc 1. It's going to be a rate of change, or it's going to be a slope of a tangent line, or something like that. Whenever you get stuck on any of these new concepts, go back and try to imagine what was going on with the one dimension, or the one variable version of all this, because it's mostly the same. Now, granted, there will be some extra complications and nuances and things like that, but the overall idea will be the same. All right, so anyways, that's kind of my my general overview of what to expect for Calculus 3. And as some people mentioned, this is not on the notes. This is just something I wanted to tell you guys so we know what we're actually going to be doing this semester. Now I'm going to begin actually going over the lecture notes. I said we're going to do new material today, and that is true. So we're going to start by doing our lecture 1 notes. Lecture 1. Lecture 1 is entitled 3D Rectangular Coordinate System. All right, so let's see here. So as I said earlier, and I kind of drew this picture already, we're already used to dealing with things in the XY plane. X measures your horizontal difference and Y measures your vertical distance. And so if we want to plot a point, we just specify how far we go to the left or right horizontally and how far we go vertically. And the name of all of the points in this plane right here, it's called the XY plane. That's one name for it. Another thing you might see this called is this fancy R subscript, and then, or so this fancy R typeface, and then 2. This is referred to as R2 as well. Reason being is it takes 2 real lines and sort of crosses them like this. So that was old news. This was all Calculus 1. This is in the Calculus 1 column here. What we're going to be looking at is we're going to be looking at 3-dimensional space. So what we're going to do, we're going to take this XY plane and we're sort of going to slap it on the ground here. We can kind of imagine that we're taking this and we're flattening down right here. And now the x-axis is pointing this way and the y-axis is pointing this way. And this picture right here is essentially the reason why some people believe Calc 3 is harder than Calc 2, because it's not too hard to draw 2-dimensional pictures on paper. I mean, a paper is essentially 2-dimensional. But the problem is that it's substantially more difficult to draw 3-dimensional images on a 2-dimensional thing like a piece of paper. We kind of have to imagine that this is sort of poking out of the page, and there's sort of like a depth here. The way I like to imagine this is sort of like the corner of a room. So imagine this is like the corner of some kind of box-shaped room right here, and the axes go this way. Of course, just like the XY axis, we can also have the negative versions that go like this. And also, just like the XY plane, it's convenient to sometimes put these little hash marks in case we want to plot particular ones. Now, the way we do that for 3D is a bit different from 2D. We don't just put them all vertical or horizontal. For the X one, for example, we kind of have them going across diagonally like this. And the way to think about it is all of these little hash marks are going to be parallel to this y-axis right here. These are the hash marks in the x direction. The hash marks in the y direction will be just up and down like this. And then finally, the hash marks in the z direction will look. Well, anyways, this is going to be our new coordinate system, x, y, and z. All right, so another thing in common with this right here. Oh, by the way, so this is often called 3 space or R3 because we need 3 number lines that are all perpendicular in order to make this space right here. So this is R2, 2-dimensional. This is R3, 3-dimensional. Are all of these positive? Yeah, all the ones that are pointing this way, so this, and this, these are all positive right here. That brings me to my next point here. These different axes effectively carve the whole space here into 8 different what are called octants. So for example, you could have a point that has positive x, y, and z values as kind of the part coming out towards us right here, that's going to be called the first octant. Kind of like we had the different quadrants, 1, 2, 3, and 4. Right here, we're going to have 8 different octants for three-dimensional space. All right, so our first octant, this is going to be where x, y, and z are all greater than 0 or positive. This is going to be the first octant. Okay, well, how do we label the other ones? We know how to label these quadrants right here, like this. There is a way to do that, to label all 8 of these, but don't worry. The only one we're going to mention by name is the first one. So the first octant is the one where all x, y, and z are positive, and then we're not going to say like, oh, draw something in the 6th octant or anything like that. So don't worry. We only really need to know where the first one. All right, I see some chatter about this. So I said rectangular coordinate system. You may remember in Calc 2, we learned about polar coordinates. Those will be playing a role here. So we will be converting these x, y, z coordinates to other types of coordinate systems, but don't worry. That's going to be later on down the road. We'll get comfy with 3D space and the normal x, y, z coordinates, and then we'll move on to that stuff. All right, anyways, one final thing I want to introduce before I start doing some problems here is I want to introduce these 3 planes that are going to be important. So the XY plane, this actually appears in our new picture. It's essentially going to be this plane right here. So you can imagine almost this is the floor of one of the room if this was the corner of a room. This is the XY plane. And the thing that all of the points in this XY plane have in common is that Z is going to equal 0. We're not moving up or down at all. We're only moving with X's and Y's here. So that's the XY plane. And just in the same way we have the XY plane, we could also have the XZ plane right here. And what do you think the condition is that all the points on here share for XZ? You could go ahead and spam the chat with that. What do you think all of these points in the XZ plane have in common? There we go. Y is equal to 0. That's right. We don't care what Y is really, so we're just going to set it equal to 0. The only thing that could be different are these X's and Z's. And then finally, the last different plane we have, so the XZ and then the YZ plane, you can imagine these as like the walls of the room where this is a corner. And on this one, we're going to have that X is equal to 0. So the way to remember this is the variable that wasn't mentioned in the name of the plane, that's going to equal 0. And we'll be mentioning these a lot, XZ, YZ, and XY. So it's important to be familiar with what these are. And finally, I didn't want to draw it this way because it gets a little bit too complicated, but these also include all of the negative values. So technically, I could extend my drawing down here if I wanted to and include negative Z values, for example. So that's also allowed. All right, anyways, so we got a bunch of terminology going here. So let's do some examples. Let's try to put some actual numbers in here. So I want us to plot 2 points. Point 1 is going to be the point 2, 3, negative 2. And then the second point is going to be 0, negative 1, and 2. So we're just going to try and plot these points. I'm going to draw my axes here. Draw a few hash marks. And in the beginning, I'm going to label these as X, Y, and Z pretty religiously, but once we get more and more comfortable with this and which one is which, then I might drop the labels. All right, let's see. So point 1. So that means we go, and by the way the way this is labeled is exactly the way you expect. We have X is the first one, just like with 2D. Y is the second one, just like 2D. But then the third coordinate here is going to be our new Z coordinate. So this represents the X, Y, and Z coordinate of these points. All right, anyways, let's see. So point 1, so we have X is 2, so that means I start at the origin, go 2 in this direction. Let's see, Y is going to be 3, so I from here move 3 in the Y direction, and then Z is negative 2, so I kind of move downwards 2. And there we are, so there is my point. Now, it's kind of difficult to tell, for example, that this isn't in the XY plane. This is lower than the XY plane. And that's where some of the difficulty comes in. We kind of need to imagine the 3D image. And this is kind of pointing downwards, the line connecting this to the origin. All right. So that's our first point. This is P1. And then let's try to figure out where P2 is. So we start off by going 0 in the x direction. So we're not going to go in the x direction at all. We go -1 in the y direction. So rather than going this way, I go this way. And then I go up 2 in the z direction. So it looks like my point is going to be right here. It's going to pop out this way. And it looks like these are on the same line right here, but technically they're not. There's technically an angle that's not 180 degrees in between those two. How'd I get 2 down for z? So I did 2 this way, and I did 3 in the y direction, and then I moved down 2 like this. So once I did my x and my y, then I just moved up or down based on what my z is. So I was here, and then I moved down 2 for my -2 for z. All right, great. So we have these points in the plane, and I think I'm pretty confident you guys can plot any points you want. You've seen this example. Okay, now it's pretty clear that we can have, oops, there's my reminder to record. Let me get another piece of paper here. Let's see here. Why is the y horizontal and x coming out of the page? That's just kind of the standard labeling for this. So we can kind of imagine that we take this XY picture and we kind of just throw it on the floor and twist it a little bit. You could technically draw the axes in a different way, but we'll talk more about that later. All right, let's see here. So since we have more than one point in the plane right here, naturally we may ask, okay, what are the distance between 2 points? So back in Calc 1, or even earlier technically, the distance between x, y, and maybe another point AB is going to be the square root of x minus a squared plus y minus b squared. And what theorem did this come from? So this looks a lot like what theorem? This distance formula. The Pythagorean theorem, that's right. So that's how we would show that this is the distance, is by using the Pythagorean theorem. And the hypotenuse squared is the sum of the two sides squared. All right, now let's move on to Calc 3. And just as I promised earlier on, this is going to be almost exactly the same as it was in Calc 1, only we're throwing in a z as well. Let's say we want to know the distance between x, y, z and a, b, and c. All right, so let's see here. The x and y's are going to be identical. X minus a squared, y minus b squared. And then I bet you guys could probably guess what's going to come next, since we have our third variable, and those could be different as well. We're going to have z minus c squared. And also, just like the one we used in Calculus 1, both of these come from the Pythagorean theorem. If you wanted to prove these equations right here, they both come from the Pythagorean theorem and drawing triangles in either our space here for Calc 3 or in our plane for Calc 1. Unfortunately, time doesn't permit me to go over that detail, but it comes from the Pythagorean theorem. All right, so as an example here, sorry, let me get my page up. So let's find the distance between the 2 points, P1 and P2, that we had earlier. P1 was 2, 3, -2, and P2 is 0, -1, and 2. All right, so if we want to find the distance d between them, well, we do this coordinate minus this coordinate, so 2 minus 0, we square it. We do 3 minus -1, so that's going to be 3 minus -1 squared. And then we have -2 minus 2, and that will be squared. All right, well, let's see here. Let's simplify this. 2 minus 0 is 2. Let me square that to get 4. 3 minus -1 is 4, and then we square that to get 16. And then -2 minus 2 is -4, and we square that to get 16 once again. And then we do the arithmetic here. This is the square root of 36, aka 6. So these points have a distance 6 apart from one another when plotted in, or sorry, not the plane, in 3D space. All right. Now, what we can also measure is not only distance between 2 points, but we could also measure the distance between a point and, say, the XY plane. So in another example here, we're going to try to find the distance from 1, -2, 3 to a bunch of different things here. What would the units of 6 be? We're not really doing any units right now. It'd be units of distance or length if you were doing physics. We don't need to worry about distance. Is the 6 away from each other or from all of them simultaneously? This point right here is 6 away from this point right here. That's what we were saying. All right, so anyways, I want to go over these examples here. So I want to find the distance from this to the xy plane. Now you might be thinking, okay, let's draw the picture here. So let's see. So we have x, y, and z. Oh, by the way, so I'm really bad about like accidentally writing down here off the camera. If I ever do this, like I'm writing down something here and you can't see it, just spam the chat with up. That was kind of the system that we came up with before. So please feel free to spam the chat with that if I'm accidentally writing down too far. Although I noticed that people were last semester were doing it even if I was like this, they just wanted to have all this blank space here. Please don't do it unless I'm actually writing off screen. All right, so we have 1. All right, and then we go in the y direction, -2. All right, that looks good. And then we go up in the z direction, 3. So from here we go up 1, 2, 3. So there's our point. This is the point that we're going to find the distance from to things here. All right, so the xy plane, so that's this. And then it could also go in this direction as well. Now, one thing to ask yourself is that this plane has a lot of different points. So maybe if I want to go from here to say this point in the plane, it'd be this distance. But then maybe I want to go to the closest point, and that'd be right here. Maybe I want to go to this point. And all of these are different distances from the point. So which one am I really asking about if I ask from the distance from a point to the plane? And the answer is we always want the shortest distance. So if you're asked the distance from a point to a plane or maybe a line or something like that, you always want to select the shortest one, in which case the shortest one would be just dropping this point directly downwards to the xy plane. All right, now what was the equation that we had for the xy plane? What was kind of the characteristic that all of the points in the xy plane shared? That's right. So the xy plane is equivalent to all the points where z is equal to 0. Now, the only thing they have to have in common is z equals 0. The x and y's can be whatever we want, but z has to be 0. Thus, in order to move this point from here to the xy axis, we simply need to change this so that z is 0. So I effectively want to move this point to 1, -2, and 0, because I don't care what x and y are. I just want my z to be 0. So in the case here, if I do the distance formula, that's going to be the square root of 1 minus 1 squared, and then -2 minus -2 squared, and then 3 minus 0 squared. And as you might expect, and as people were already saying in the chat here, all of these are going to be 0, and I'm really just ending up with the square root of 9 or 3. If you want to know the distance from a point to the plane, you pick the shortest one. And for the xy, yz, and zy planes, you simply just need to set the appropriate coordinate to be 0, and however far you need to move to be that's going to be it. So distance would be absolute value z? Yes, it would. So if I were to say at the point -3, I went down here instead, that would still be 3 away. Absolutely. All right, let's test this reasoning on the other planes. Let's try this on the yz plane. Okay, so without even doing any work here, remember the yz plane has x equals 0, right? So how far away will this point be from the plane where x is 0? What's the distance here? You can spam the chat with it. That's right, it's going to be 1. Because all we need to do, we don't care about what the y and z coordinates are. We simply need to make x be 0. That's the only thing that all these points have to have in common. So the distance from this point to the plane is going to be 1. All right, and then in pretty much exactly the same way, why don't we do this one real quick? Why don't we take a look at the xz plane? All right. So the xz plane, what's that distance going to be? That's right. It's going to be 2 because I need to go from -2 to 0, and that's a distance of 2. Okay. Now, we can also ask these questions about axes. So we can figure out the amount of distance from this point to say maybe the z-axis right here. It's going to be a little bit different, but it's still not going to be too bad. So for example, let's say we want to know the distance from this point right here to the x-axis. That's this right here. All right, and then just like we had these kind of equations that made up the planes, we also have equations that make up our axes as well. Now, the thing in common with everything on the x-axis is that our z is going to be 0. We're not up and down in any way. And our y is going to be 0. We're not left or right in any way. So the x-axis means that both y and z need to be 0. So this is the condition to make the x-axis. So we're not in y and z at all. We're simply just along here. So that means that when we do our distance formula here, really finding the distance, we don't care what the x is, so we can just have that be the same. And we're going to have -2 minus 0, and then 3 minus 0. Because remember, we want the y and z to be 0, but then the x doesn't matter at all. All right, so then this will be 0. We have -2 squared will be 4, and then we have 3 squared will be 9. So we don't get a natural number here, we get root 13 for that distance. All right, and then we can do a similar calculation with the y-axis. All right, so then we have x and z are going to be 0 for this one, since we're not up or down or in or out for that. So our distance then will be 1 minus 0 squared. The y doesn't matter, so that's going to be the same. We have 3 minus 0 squared. All right, so this will be the square root of 1 plus 9 is root 10. All right, and for the sake of time here, I knew today was going to be a tight schedule. It already looks like we're starting to run a little low on time here. I'm going to leave F to you guys. So on your own, maybe, why don't you try to see how far this is from the z-axis? But spoiler alert, it's going to be almost exactly the same as it was for these guys right here. You want your x and y. 0. Okay. Let's move on here. So back in Calc 1 and back in the 2D world, there was a specific name for all of the points that were a certain distance away from a fixed point called the center. What is the name of this shape right here? It's a circle, and in this case, it kind of looks like it's the unit circle. And remember, the circle is all the points that are a fixed distance away from a center. So there's a 3D version of this, obviously. So now, kind of imagine that we have all of the points maybe 1 away from the origin here in 3D space. What do you think the name for this is going to be? Going to be a sphere. That's right. So this is going to be a sphere right here. And just in the same way that the circle had the equation x minus h squared plus y minus k squared is r squared, where this was the center, the formula for a sphere is going to be pretty much the same way. It's going to be x minus a squared plus y minus b squared plus z minus c squared is r squared. And we have a center of a, b, and c, and a radius of r. All right, and you'll notice that this kind of looks similar to the distance formula. The way to get from here to the distance formula is simply to take the square root. That's saying that we want all of these points to be a distance r away from a, b, c. All right, so that's the general formula for a sphere. Now let's do a problem with this. So here's another example here. Okay, so find the equation of a sphere which has the line connecting our P1 and P2 from earlier. So 2, 3, -2, and 0, -1 and 2 as the diameter. Okay, so what this is saying is we have these 2 points, right? Let's draw them real quickly. Practice doing this. All right. We have X, we have Y, and we have Z. All right, let's see. So we have 2, and then it looks like we have 3. So that means we're right here. And then we go down to 1, 2. This is going to be our first point, which I'll call P1. And then our second point is going to be 0, -1, and then I go up 2, right here. This is P2. What we're saying is that we have a straight line, and this is moving through three-dimensional space, this line, connecting these, and this is the diameter of the circle. So this, or sorry, the diameter of the sphere. I'm going to keep saying two-dimensional shapes by mistake, so forgive me. So we're having a sphere that's connecting these guys. And then this is the diameter right here. So if it were a globe, you can almost imagine this is sort of like the axis that goes through the globe. That means that the center of the sphere is going to be halfway in between these 2 points right here. So if this is P1 and P2, that means that the center is going to be halfway between them. All right, so let's see. So that means that our center, what's the coordinate for that? Well, what's halfway between 0 and 2 right here? It's going to be 1. What's going to be halfway in between -1 and 3? Well, they have a distance of 4. Divide that by 2 and add it to this. So we have 1 for that. And then the distance from -2 to 2, halfway in between that, will be 0. All right, so this is going to be the center of our sphere. The diameter is bent. No, this is a perfectly straight line connecting. I'm sorry, my drawing's not very good. I intended for this to be entirely straight. All right. Anyways, we got the center here. So that means we're going to have x minus 1 squared plus y minus 1 squared. And then we have 0, so we might as well just leave it as z squared. Now, what we need to figure out is what is the radius of this sphere? Well, the length of this line is the diameter, right? So if we divide the length of this line, or the distance between these points, by 2, then we're going to get the radius. And I think, if I'm not mistaken, we already found the distance between these guys back here, if I'm not mistaken. Yeah, we did. So this is the distance between these. We found that that was 6. So if we go back down here, this whole distance of this line is 6, meaning the diameter is 6. That means our radius will be 3. And we have 3 squared right here. And this is going to be our sphere right there. How could this is the sphere tilted? Well, technically the sphere doesn't care which way you rotate it. This is simply one axis of many different axes here. So this is an axis. I could potentially draw something like this, or maybe something like this. All of those are axes, and the sphere is going to look the same no matter which one I'm using. So it's just going to be a ball in all cases. All right, I'm going to do another problem here. Okay, so find the center and radius of this sphere. X squared plus y squared plus z squared minus 2x plus 6y minus 8z is -1. Now, this may not look like it, but this is actually the equation of a sphere. And Charlotte has the right idea here. The way we're going to make it look more like this is we're going to complete the square. All right, so I'm going to gather together the matching terms here. I have x squared minus 2x. I'm going to complete the square with that. I have y squared plus 6y. I'm going to complete the square there. And then I have z squared minus 8z. All right, now let's remember back the way to complete the square here. We take whatever this number is, divide it by 2, and square it. And then we're going to add that number to both sides. So in this case, I divide this by 2 and get -1. I square that and get +1. So I'm adding in a +1 here. meaning I'm going to have to add a positive 1 to that side as well. And then we do the same thing with our y. 6 over 2 is 3. We square that and get 9. All right, so I'm going to add 9 to both sides because I added it right there. And then finally, we have z squared minus 8z. Let's see, I divide 8 by 4, or sorry, 8 by 2 to get negative 4. I square that to get 16. I have to add that to both sides since I added it over here. All righty. Oh yeah, Gillen actually has a good point here. So a lot of variables look like numbers. In particular, 2 looks a lot like z. So watch out for that. So whenever I write my z's, I'm going to put this line through it to distinguish it from a 2. Because if I don't do that, then you're going to start seeing things like this, which will be very confusing. So I encourage you, all of you, to put lines through your z's to make it look. All right, anyways, let's finish this off here. If I factor that, I get this. If I do the factoring here, this is what I get. And same thing here. And then I sum all of these together and get 25. This means that my radius is 5, and my center will be 1, -3, and 4. Remember, the center is minus each of these numbers, so I have to flip the sign of all of them. All right, so let's not forget about completing the square. This showed us that this equation, while it didn't look like it, was actually an equation of the sphere. All right, oh my goodness. I knew today was going to be jam-packed, but it looks like we're actually out of time right now. There were a few more questions that I wanted to go over in here. What I'm going to do is I'm going to post kind of filled in lecture notes with only those questions. So the stuff that I didn't get to that was after this, I'm going to post that on Canvas. So let me show you where that's going to be. Let me share my internet again. Let's see here. So there's this page here that says Dr. Ian Manley, and there's this lecture. If you click this link, then you'll see the recordings link down here starting on Friday. And I'm also going to put a link to the completed lecture notes that we don't get to in class here. So I apologize for not making it today. Today was kind of rough because we also had to go over the syllabus here. All right, well, that about does it for today. Let me stop the recording here. Let's see.